The history of mathematics is the story of the discoveries in mathematics and the mathematical methods and notation of the past. Before the modern age and the worldwide spread of knowledge, written examples of new mathematical developments have only been found in a few locations. From 3000 BCE, the Mesopotamian states of Sumer, Akkad, and Assyria, followed closely by ancient Egypt and the Levantine state of Ebla, began using arithmetic, algebra, and geometry for purposes of taxation, commerce, trade, and also in the patterns in nature, the field of astronomy, and to record time and formulate calendars. The earliest mathematical texts available are from Mesopotamia and Egypt. These include Plimpton 322, Babylonian c. 2000, 1900 BCE, the Rhind Mathematical Papyrus, Egyptian c. 1800 BCE, and the Moscow Mathematical Papyrus, Egyptian c. 1890 BCE. All of these texts mention the so-called Pythagorean triples, so it is clear that the Pythagorean theorem is the most ancient and widespread mathematical development after basic arithmetic and geometry. The study of mathematics as a demonstrative discipline began in the 6th century BCE with the Pythagoreans, who coined the term mathematics from the ancient Greek mathema, meaning subject of instruction. Greek mathematics refined methods, especially through the introduction of deductive reasoning and mathematical rigor in proofs, and expanded the subject matter of mathematics. The ancient Romans made significant contributions to applied mathematics, which they used in surveying, structural engineering, mechanical engineering, bookkeeping, the creation of lunar and solar calendars, and even arts and crafts. Chinese mathematics made early contributions, including a place value system and the first use of negative numbers. The Hindu-Arabic numeral system and the rules for the use of its operations, in use throughout the world today, evolved over the course of the first millennium CE in India and were transmitted to the Western world via Islamic mathematics through the work of Muhammad ibn Musa al-Khwarizm. It is clear that Chinese mathematics developed and expanded the mathematics known to these civilizations. The mathematics developed by the Maya civilization of Mexico and Central America, where the concept of zero was given a standard symbol in Maya numerals, was contemporaneous with but independent of these traditions. Many Greek and Arabic texts on mathematics were translated into Latin from the 12th century onward, leading to further development of mathematics in medieval Europe. From ancient times through the Middle Ages, periods of mathematical discovery were often followed by centuries of stagnation. This changed in Renaissance Italy in the 15th century, where new mathematical developments, interacting with new scientific discoveries, were made at an increasing pace that continues through the present day. This includes the groundbreaking work of both Isaac Newton and Gottfried Wilhelm Leibniz in the development of infinitesimal calculus during the course of the 17th century. Abacus. The abacus, plural abaci or abacuses, also called a counting frame, is a calculating tool which has been used since ancient times. It was used in the ancient Near East, Europe, China, and Russia, millennia before the adoption of the Hindu-Arabic numeral system. The exact origin of the abacus has not yet emerged. It is a device made up of rows of movable beads or similar objects strung on a wire. These beads represent digits. One of the two numbers is set up, and the beads are manipulated to perform an operation such as addition or even a square or cubic root. The Sumerian abacus appeared between 2700 and 2300 BCE. It held a table of successive columns, which delimited the successive orders of magnitude of their sexagesimal, base 60 number system. Old Babylonian mathematics. Babylonian mathematics were written using a sexagesimal, base 60 numeral system. This is the origin of the modern-day usage of 60 seconds in a minute, 60 minutes in an hour, and 360, 60 x 6 degrees in a circle, as well as the use of seconds and minutes of arc to denote fractions of a degree. The Babylonians chose the sexagesimal system because 60 can be evenly divided by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. Unlike the Egyptians, Greeks, and Romans, the Babylonians had a place value system where digits written in the left column represented larger values. This is similar to the decimal system. The Babylonian notational system was the best of any civilization until the Renaissance. It could be used to represent fractions as easily as whole numbers. This meant that multiplying two numbers that contained fractions was no different from multiplying integers. This is similar to modern notation. The notational system of the Babylonians was the best of any civilization until the Renaissance. Its power allowed it to achieve remarkable computational accuracy. For example, the Babylonian tablet YBC 7289 gives an approximation of 2 accurate to 5 decimal places. However, the Babylonians lacked an equivalent of the decimal point, so the place value of a symbol often had to be inferred from the context. By the Seleucid period, the Babylonians had developed a zero symbol as a placeholder for empty positions, but it was only used for intermediate positions. The Babylonians came close to developing a true place value system, but they did not succeed. This zero sign does not appear in terminal positions, so they did not have the necessary tools to achieve this. Other topics covered by Babylonian mathematics include fractions, algebra, quadratic and cubic equations, and the calculation of regular numbers and their reciprocal pairs. The tablets also include multiplication tables and methods for solving linear, quadratic equations and cubic equations, a remarkable achievement for the time. Tablets from the Old Babylonian period contain the earliest known statement of the Pythagorean theorem. However, as with Egyptian mathematics, Babylonian mathematics shows no awareness of the difference between exact and approximate solutions or the solvability of a problem, and most importantly, no explicit statement of the need for proofs or logical principles. The Babylonians used a form of Fourier analysis to compute an ephemeris, table of astronomical positions, which was discovered in the 1950s by Otto Neugebauer. To make calculations of the movements of celestial bodies, the Babylonians used basic arithmetic and a coordinate system based on the ecliptic, the part of the heavens that the sun and planets travel through. Thales's theorem. Greek mathematics is said to have begun with Thales of Miletus, c. 624–548 BCE. Little is known about his life, but it is generally agreed that he was one of the 7 wise men of Greece. Proclus states that Thales traveled to Babylon, where he learned mathematics and other subjects. He then came up with the proof of what is now called Thales's theorem. Thales used geometry to solve problems such as calculating the height of pyramids and the distance of ships from the shore. He is credited with the first use of deductive reasoning applied to geometry by deriving 4 corollaries to Thales's theorem. He is therefore hailed as the first true mathematician and the first known individual to whom a mathematical discovery has been attributed. Pythagoras. Pythagoras of Samos, c. 580–500 BCE, is another enigmatic figure. He supposedly visited Egypt and Babylon and ultimately settled in Croton, Magna Graecia, where he started a kind of brotherhood. Pythagoreans believed that all is number and were keen in looking for mathematical relations between numbers and things. Pythagoras himself was given credit for many later discoveries, including the construction of the 5 regular solids. Almost half of the material in Euclid's Elements is customarily attributed to the Pythagoreans. This includes the discovery of irrationals, which is attributed to Hippasus, c. 530–450 BCE, and Theodorus, Phlos 450 BCE. It was the Pythagoreans who coined the term mathematics, and with whom the study of mathematics for its own sake begins. The greatest mathematician associated with the group was undoubtedly Archytas, c. 435–360 BCE. He solved the problem of doubling the cube, identified the harmonic mean, and possibly contributed to optics and mechanics. Other mathematicians active in this period included not affiliated with any school, These mathematicians include Hippocrates of Chios, c. 470-410 BCE, Theaetetus, c. 417-369 BCE, and Eudoxus, c. 408-355 BCE. The discovery of irrational numbers is attributed to a Pythagorean, possibly Hippasus of Metapontum. He probably discovered them while identifying sides of the pentagram. The then-current Pythagorean method claimed that there must be a sufficiently small indivisible unit that could fit evenly into one of these lengths as well as the other. Hippasus, in the 5th century BCE, was able to prove that there was no common unit of measure and that the assertion of such an existence was a contradiction. Greek mathematicians called this ratio of incommensurable magnitudes alogos, or inexpressible. Hippasus was not celebrated for his discovery. One legend says he made it while out at sea and was thrown overboard by his fellow Pythagoreans for challenging their beliefs. The doctrine that all phenomena in the universe can be reduced to whole numbers and their ratios. Whatever the consequence to Hippasus himself, his discovery posed a very serious problem to Pythagorean mathematics, since it shattered the assumption that number and geometry were inseparable, a foundation of their theory. Plato. Plato is a key figure in the history of mathematics, inspiring and guiding others. His Platonic Academy in Athens became the mathematical center of the world in the 4th century BCE, and it was from this school that the leading mathematicians of the day, such as Eudoxus of Cnidus, emerged. Plato also discussed the foundations of mathematics, clarified some of the definitions, e.g. that of a line as breadthless length, and reorganized the assumptions. The analytic method is ascribed to Plato, while a formula for obtaining Pythagorean triples bears his name. Chinese geometry is the oldest existing work on the subject in China. It comes from the philosophical Mohist canon, compiled by the followers of Mozi, 470-390 BCE. The Mojing described various aspects of many fields associated with physical science and provided a small number of geometrical theorems as well. It also defined the concepts of circumference, diameter, radius, and volume. Chinese decimal system. The Tsinghua bamboo slips, containing the earliest known decimal multiplication table, although the oldest surviving mathematical text of China is the ancient Babylonian text, dated around 305 BCE. It is notable for its use of a decimal positional notation system, the so-called rod numerals, in which distinct ciphers were used for numbers between 1 and 10. The number 123 would be written using the symbol for 1, followed by the symbol for 100, then the symbol for 2, followed by the symbol for 10, followed by the symbol for 3. This was the most advanced number system in the world at the time. It was apparently in use several centuries before the Common Era and well before the development of the Indian numeral system. Rod numerals allowed the representation of numbers as large as desired and allowed calculations to be carried out on the swan pan, or Chinese abacus. It is presumed that officials used the multiplication table to calculate land surface area, yields of crops, and the amounts of taxes owed. Hellenistic Greek mathematics. The Hellenistic era began in the late 4th century BCE, following Alexander the Great's conquest of the eastern Mediterranean, Egypt, Mesopotamia, the Iranian plateau, Central Asia, and parts of India. This led to the spread of the Greek language and culture across these regions. Greek became the lingua franca of scholarship throughout the Hellenistic world, and the mathematics of the classical period merged with Egyptian and Babylonian mathematics to give rise to Hellenistic mathematics. Greek mathematics and astronomy reached its acme during the Hellenistic and early Roman periods, and much of the work represented by authors such as Euclid, around 300 BCE, Archimedes, around 287-212 BCE, Apollonius, c. 240-190 BCE, Hipparchus, c. 190-120 BCE, and Ptolemy, c. 100-170 CE, was of a very advanced level and rarely mastered outside a small circle. The work of Eades, c. 287-212 BCE, Apollonius, c. 240-190 BCE, Hipparchus, c. 190-120 BCE, and Ptolemy, c. 100-170 CE, was of an extremely advanced level and was rarely mastered outside a small circle. Several centers of learning. The Hellenistic period saw the emergence of several centers of learning, the most significant of which was the Mauseion in Alexandria, Egypt. This institution attracted scholars from across the Hellenistic world, with the majority being Greek, but also including Egyptian, Jewish, and Persian scholars. Despite their small numbers, Hellenistic mathematicians actively communicated with each other, with publication consisting of passing and copying someone's work among colleagues. Euclid. In the 3rd century BCE, the Museum of Alexandria was the premier center of mathematical education and research. It was there that Euclid, c. 300 BCE, taught and wrote the Elements, which were widely considered the most successful and influential textbook of all time. The Elements is the most successful and influential textbook of all time. Euclid is the father of geometry and is chiefly known for this treatise, which established the foundations of geometry that largely dominated the field until the early 19th century. His system, now known as Euclidean geometry, introduced new innovations and combined theories from earlier Greek mathematicians, including Eudoxus of Cnidus, Hippocrates of Chios, Thales, and Theaetetus. Euclid is undoubtedly one of the greatest mathematicians of antiquity, alongside Archimedes and Apollonius of Perga. His Elements introduced mathematical rigor through the axiomatic method and is the earliest example of the format still used in mathematics today, that of definition, axiom, theorem, and proof. Although most of the contents of the Elements were already known, Euclid arranged them into a single, coherent logical framework. This was an introductory textbook to all mathematical subjects of the time, including number theory, algebra, and solid geometry. It included proofs that the square root of 2 is irrational and that there are infinitely many prime numbers. Euclid also wrote extensively on other subjects, such as conic sections, optics, spherical geometry, and mechanics. However, only half of his writings survive. The Euclidean algorithm is one of the oldest algorithms in common use. Euclid's Elements, c. 300 BCE, contains the algorithm, specifically in Book 7, Propositions 1 to 2, and Book 10, Propositions 2 to 3. In Book 7, the algorithm is formulated for integers, whereas in Book 10, it is formulated for lengths of line segments. Centuries later, Euclid's algorithm was discovered independently in India and China. It was used to solve Diophantine equations that arose in astronomy and to make accurate calendars. Archimedes. There is no doubt that Archimedes of Syracuse is regarded as one of the leading scientists in classical antiquity. There is no doubt that Archimedes was the greatest mathematician of ancient history and one of the greatest of all time. He anticipated modern calculus and analysis by applying the concept of the infinitely small and the method of exhaustion to derive and rigorously prove a range of geometrical theorems. These include the area of a circle, the surface area and volume of a sphere, the area of an ellipse. He also calculated the area under a parabola, the volume of a segment of a paraboloid of revolution, the volume of a segment of a hyperboloid of revolution, and the area of a spiral. Archimedes' other mathematical achievements include deriving an approximation of pi, defining and investigating the Archimedean spiral, and devising a system using exponentiation for expressing very large numbers. He was also one of the first to apply mathematics to physical phenomena, working on statics and hydrostatics. Archimedes' achievements in this area include a proof of the law of the lever, the widespread use of the concept of center of gravity, and the enunciation of the law of buoyancy or Archimedes' principle. Despite orders that he should not be harmed, Archimedes was killed during the siege of Syracuse by a Roman soldier. Apollonius's parabola. Apollonius of Perga, c. 262-190 BCE, made significant advances to the study of conic sections. He demonstrated that one can obtain all three varieties of conic section by varying the angle of the plane that cuts a double-napped cone. He also coined the terminology in use today for conic sections, namely parabola, place beside or comparison, ellipse, deficiency, and hyperbola, a throw beyond. His work, Conics, is one of the best-known and most preserved mathematical works from antiquity. It contains many valuable theorems concerning conic sections that would prove invaluable to later mathematicians and astronomers studying planetary motion, such as Isaac Newton. It is clear that neither Apollonius nor any other Greek mathematicians made the leap to coordinate geometry. However, Apollonius's treatment of curves is in some ways similar to the modern treatment, and some of his work seems to anticipate the development of analytical geometry by Descartes, some 1800 years later. Archimedes. There is no doubt that Archimedes of Syracuse is regarded as one of the leading scientists in classical antiquity. There is no doubt that Archimedes was the greatest mathematician of ancient history and one of the greatest of all time. He anticipated modern calculus and analysis by applying the concept of the infinitely small and the method of exhaustion to derive and rigorously prove a range of geometrical theorems. These include the area of a circle, the surface area, and volume of a sphere, the area of an ellipse. He also calculated the area under a parabola, the volume of a segment of a paraboloid of revolution, the volume of a segment of a hyperboloid of revolution, and the area of a spiral. Archimedes' other mathematical achievements include deriving an approximation of pi, defining and investigating the Archimedean spiral, and devising a system using exponentiation for expressing very large numbers. He was also one of the first to apply mathematics to physical phenomena, working on statics and hydrostatics. Archimedes' achievements in this area include a proof of the law of the lever, the widespread use of the concept of center of gravity, and the enunciation of the law of buoyancy, or Archimedes' principle. Despite orders that he should not be harmed, Archimedes was killed during the siege of Syracuse by a Roman soldier. Apollonius's parabola. Apollonius of Perga, c. 262–990 BCE, made significant advances to the study of conic sections. He showed that one can obtain all three varieties of conic section by varying the angle of the plane that cuts a double-napped cone. He also coined the terminology in use. Today, we use the terms parabola, ellipse, and hyperbola to describe conic sections. These terms were first used by Apollonius of Perga, who is considered one of the most influential mathematicians in antiquity. His work, Conics, is one of the best preserved mathematical texts from that period and contains many valuable insights into conic sections. These insights proved invaluable to later mathematicians and astronomers, including Isaac Newton. Astronomers studying planetary motion, such as Isaac Newton. While neither Apollonius nor any other Greek mathematicians made the leap to coordinate geometry, Apollonius's treatment of curves is in some ways similar to the modern treatment, and some of his work seems to anticipate the development of analytical geometry by Descartes some 1800 years later. 9 chapters on the mathematical art. In 212 BCE, the emperor Qin Shi Huang commanded all books in the Qin Empire other than officially sanctioned ones be burned. This decree was not universally obeyed, but as a consequence of this order, little is known about ancient Chinese mathematics before this date. After the book burning of 212 BCE, the Han Dynasty, 202 BCE, 220 CE, produced works of mathematics which expanded on works that are now lost. The most important of these is the 9 chapters on the mathematical art, which was first published in CE 179, but existed in part under other titles beforehand. It consists of 246 word problems, including those involving agriculture, business, the employment of geometry to figure height spans and dimension ratios for Chinese pagoda towers, engineering, surveying, and material on right triangles. It created mathematical proof for the Pythagorean theorem and a mathematical formula for Gaussian elimination. The treatise, it also provides values of p, which Chinese mathematicians originally approximated as 3, until Liu Xin, D23 CE, provided a figure of 3.1457, and subsequently Zhang Heng, 78-139, approximated pi as 3.724, 162 by taking the square root of 10. Negative numbers first appeared in history in the 9 chapters on the mathematical art, but they may well contain much older material. The mathematician Liu Hui, c. 3rd century, established rules for the addition and subtraction of negative numbers. Hipparchus and trigonometry. The 3rd century BCE is indisputably the golden age of Greek mathematics, with advances in pure mathematics henceforth in relative decline. Nevertheless, in the centuries that followed, significant advances were made in applied mathematics, most notably trigonometry, to address Hipparchus of Nicaea, c. 190–120 BCE, is the founder of trigonometry. He compiled the first known trigonometric table, and is also responsible for the systematic use of the 360-degree circle, Almagest of Ptolemy. In the 2nd century CE, the Greco-Egyptian astronomer Ptolemy, from Alexandria, Egypt, constructed detailed trigonometric tables, Ptolemy's Table of Chords, in Book 1, Chapter 11 of his Almagest. Ptolemy used chord length to define his trigonometric functions, a minor difference from the sign convention we use today. Centuries passed before more detailed tables were produced, and Ptolemy's treatise remained in use for performing trigonometric calculations in astronomy throughout the next 1200 years in the medieval Byzantine, Islamic, and, later, Western European worlds. Ptolemy is also credited with Ptolemy's theorem for deriving trigonometric quantities and the most accurate value of p outside of China until the medieval period, 1416. The Chinese remainder theorem is a mathematical theorem that states that if one knows the remainders of the Euclidean division of an integer n by several integers, then one can determine the remainder of the division of n by the product of these integers, under the condition that the divisors are pairwise coprime. No two divisors share a common factor other than 1. The earliest known statement of the theorem is by the Chinese mathematician Sun Tzu in the Sun Tzu Xuanqing in the 3rd century CE Diophantine analysis. Following a period of stagnation after Ptolemy, the period between 250 and 350 CE is often referred to as the Silver Age of Greek mathematics. During this period, Diophantus made significant advances in algebra, particularly in indeterminate analysis, which is also known as Diophantine analysis. The study of Diophantine equations and Diophantine approximations is a significant area of research to this day. His main work was the Arithmetica, a collection of 150 algebraic problems dealing with exact solutions to determinate and indeterminate equations. The Arithmetica had a significant influence on later mathematicians, such as Pierre de Fermat, who arrived at his famous last theorem. After trying to generalize a problem he had read in the Arithmetica, that of dividing a square into 2 squares, Diophantus made significant advances in notation. The Arithmetica was the first instance of algebraic symbolism and syncopation. Story of 0. Ancient Egyptian numerals were of base 10. They used hieroglyphs for the digits and were not positional. By the middle of the 2nd millennium BCE, the Babylonian mathematics had a sophisticated base 60 positional numeral system. There was no positional value, or 0, in the Babylonian system. This was indicated by a space between sexagesimal numerals. The Mesoamerican long count calendar developed in south-central Mexico and Central America required the use of 0 as a placeholder within its vigesimal base 20 positional numeral system. The concept of 0 as a written digit in the decimal place value notation was developed in India. A symbol for 0, a large dot, likely to be the precursor of the still current hollow symbol, is used throughout the B. The Akshali manuscript is a practical manual on arithmetic for merchants. Radiocarbon dating has shown that 3 samples from the manuscript come from 3 different centuries: CE 224-383, CE 680-779, and CE 885-993. This makes it South Asia's oldest recorded use of the 0 symbol. It is not known how the birch bark fragments from different centuries forming the manuscript came to be packaged together. Rules governing the use of 0 appeared in Brahmagupta's Brahmasputra Siddhanta, 7th century, which states the sum of 0 with itself as 0 and incorrectly divides by 0 as a positive or negative number when divided by 0 is a fraction with the 0 as denominator. 0 divided by a negative or positive number is either 0 or expressed as a fraction with 0 as the numerator and the finite quantity as the denominator. 0 divided by 0 is 0. Hypatia. The first woman mathematician recorded by history was Hypatia of Alexandria, CE 350-415. She wrote many works on applied mathematics. For political reasons, the Christian community in Alexandria had her stripped publicly and executed. Her death marks the end of the era of Alexandrian Greek mathematics. However, work did continue in Athens for another century with figures such as Proclus, Simplicius, and Eutocius. While Proclus and Simplicius were more philosophers than mathematicians, their commentaries on earlier works are valuable sources on Greek mathematics. The closure of the Neoplatonic Academy of Athens by the Emperor Justinian in 529 CE is the traditional marker for the end of the era of Greek mathematics. However, the Greek tradition continued unbroken in the Byzantine Empire, with mathematicians such as Anthemius of Tralles and Isidore of Miletus, the architects of the Hagia Sophia. Nevertheless, Byzantine mathematics consisted mostly of commentaries, with little in the way of innovation. By this time, the centers of mathematical innovation were to be found elsewhere. Indian trigonometry. The modern Sine convention is first attested in the Surya Siddhanta, which shows strong Hellenistic influence. Its properties were further documented by the 5th century CE Indian mathematician and astronomer Aryabhata. The Surya Siddhanta describes rules to calculate the motions of various planets and the moon relative to various constellations, diameters of various planets, and calculates the orbits of various astronomical bodies. The text is renowned for its pioneering discussion of sexagesimal fractions and trigonometric functions. The Indian decimal system was first described by Aryabhata in the 5th century CE. In his slim volume, the Aryabhatiya, written in verse, he set out the rules of calculation used in astronomy and mathematical mensuration. While about half of the entries are wrong, it is in the Aryabhatiya that the decimal place value system first appears. Muhammad ibn Musa al-Khwarizmi. In the 9th century, the mathematician Muhammad ibn Musa al-Khwarizmiyah wrote 2 important books on the Hindu-Arabic numerals and one on methods for solving equations. His book On the Calculation with Hindu Numerals, written around 825, along with the work of Al-Kindi, were the key to spreading Indian mathematics and Indian numerals to the West. The word algorithm is derived from the Latinization of his name, algorithmi, and the word algebra from the title of one of his works, Al-Kitab al-Mukhtasar fa-Hasab al-Ghabr wal-Muqabala, the compendious book on calculation by completion and balancing. He provided an exhaustive explanation for the algebraic solution of quadratic equations with positive roots, and he was the first to teach algebra in an elementary form and for its own sake. He also discussed the fundamental method of reduction and balancing, referring to the transposition of subtracted terms to the other side of an equation, that is, the cancellation of like terms on opposite sides of the equation. This is the operation which Al-Khwarizm originally described as algebra. His algebra was no longer concerned with a series of problems to be resolved. Instead, it started with primitive terms in which the combinations must give all possible prototypes for equations. These equations henceforth constituted the true object of study. He also studied an equation for its own sake and in a generic manner, as it does not simply emerge in the course of solving a problem, but is specifically called on to define an infinite class of problems. Abu Kamil Shuja ibn Aslam ibn Muhammad ibn Shuja was a prominent Egyptian mathematician during the Islamic Golden Age. He is the first mathematician to systematically use and accept irrational numbers as solutions and coefficients to equations. His mathematical techniques were later adopted by Fibonacci, thus allowing Abu Kamil an important part in introducing algebra to Europe. Mayan mathematics. In the pre-Columbian Americas, the Maya civilization. The Maya flourished in Mexico and Central America during the first millennium CE and developed a unique tradition of mathematics that was entirely independent of existing European, Egyptian, and Asian mathematics due to its geographic isolation. Maya numerals used a base of 20, the vigesimal system, instead of a base of 10 that forms the basis of the decimal system used by most modern cultures. The basis of the decimal system used by most modern cultures can be traced back to the Maya. They used mathematics to create the Maya calendar and to predict astronomical phenomena in their native Maya astronomy. While the concept of zero had to be inferred in the mathematics of many contemporary cultures, the Maya developed a standard symbol for it. Al-Karaji Abu Bakr Muhammad ibn al-Hassan al-Karaj was a 10th century Persian mathematician and engineer who flourished at Baghdad. He was born in Karaj, a city near Tehran. His three principal surviving works are mathematical Al-Badi fil Hisab, wonderful on calculation, Al-Fakhri fil Jabr wal Muqabala, glorious on algebra, and Al-Kafi fil Hisab, sufficient on calculation, are three of Al-Karaji's most important works. He wrote extensively on mathematics and engineering. Some regard him as merely reworking the ideas of others. He was influenced by Diophantus, but most regard him as more original, in particular for the beginnings of freeing algebra from geometry. Among historians, his most widely studied work is his algebra book Al-Fakhri fi al-Jabr wa al-Muqabala, which survives from the medieval era in at least 4 copies. His work on algebra and polynomials laid out the rules for arithmetic operations on polynomials, including addition, subtraction, and multiplication. He was unable to devise a method for dividing polynomials by monomials. Chinese algebra. The pinnacle of Chinese mathematics was reached in the 13th century during the latter half of the Song dynasty with the development of Chinese algebra. The most important text from that period is The Precious Mirror of the Four Elements by Zhu Shiji. It deals with the solution of simultaneous higher-order algebraic equations using a method similar to Horner's method. The Precious Mirror also contains a diagram of Pascal's triangle with coefficients of binomial expansions through the 8th power. Both appear in Chinese works as early as 1100. The Chinese also made use of the complex combinatorial diagram known as the magic square and magic circles, described in ancient times and perfected by Yang Hui. Japanese, Korean, and Vietnamese mathematics are traditionally viewed as stemming from Chinese mathematics and belonging to the Confucian-based East Asian cultural sphere. It is clear that Ming from Chinese mathematics and belonging to the Confucian-based East Asian cultural sphere. Korean and Japanese mathematics were heavily influenced by the algebraic works produced during China's Song dynasty, whereas Vietnamese mathematics was heavily indebted to popular works of China's Ming dynasty. For instance, Although Vietnamese mathematical treatises were written, all of them followed the Chinese format of presenting a collection of problems with algorithms for solving them, followed by numerical answers. This format was used in both Chinese and the native Vietnamese Chu Nom script. Mathematics in Vietnam and Korea were mostly associated with the professional court bureaucracy of mathematicians and astronomers, whereas in Japan it was more prevalent in the realm of private schools. Hindu-Arabic numerals. Europeans learned of Arabic numerals around the 10th century, but their spread was a gradual process. 2 centuries later, in the Algerian city of Béjaïa, the Italian scholar Fibonacci first encountered the numerals. His work was crucial in making them known throughout Europe. European trade, books, and colonialism helped popularize the adoption of Arabic numerals around the world. Arabic numerals have become a global phenomenon, used significantly beyond the contemporary spread of the Latin alphabet. They have become common in writing systems where other numeral systems existed previously, such as Chinese and Japanese numerals. The first mentions of the numerals from 1 to 9 in the West are found in the Codex Vigilanus of 976, an illuminated collection of various historical documents covering a period from antiquity to the 10th century in Hispania. Leonardo Fibonacci. In the 12th century, European scholars traveled to Spain and Sicily seeking scientific Arabic texts. These included Al-Khwarizmi's The Compendious Book on Calculation by Completion and Balancing, translated into Latin by Robert of Chester, and the complete text of Euclid's Elements, translated in various versions by Adelard of Bath, Hermann of Carinthia, and Gerard of Cremona. Versions by Adelard of Bath, Hermann of Carinthia, and Gerard of Cremona. These and other new sources sparked a renewal of mathematics. Leonardo of Pisa, now known as Fibonacci, learned about the Hindu-Arabic numerals on a trip to what is now Béjaïa, Algeria, with his merchant father. Europe was still using Roman numerals. There he observed a system of arithmetic, specifically algorithm, which, due to the positional notation of Hindu-Arabic numerals, was much more efficient and greatly facilitated commerce. He soon realized the many advantages of the Hindu-Arabic system, which, unlike the Roman numerals used at the time, allowed easy calculation using a place-value system. In 1202, Leonardo wrote Liber Abaci, which introduced the technique to Europe and began a long period of popularizing it. The book also brought to Europe what is now known as the Fibonacci sequence, which Indian mathematicians had known for hundreds of years before that. Infinite series. Greek mathematician Archimedes produced the first known summation of an infinite series with a method that is still used in the area of calculus today. He used the method of exhaustion to calculate the area under the arc of a parabola with the summation of an infinite series, and gave a remarkably accurate approximation of p. The Kerala school has made a number of contributions to the fields of infinite series and calculus. Probability theory. The modern mathematical theory of probability has its roots in the analysis of games of chance by Girolamo Cardano in the 16th century and by Pierre de Fermat and Blaise Pascal in the 17th century. For example, the problem of points. Christian Huygens published a book on the subject in 1657. In the 19th century, Pierre Laplace completed what is considered the classical definition of probability. Initially, probability theory mainly considered discrete events, and its methods were mainly combinatorial. Eventually, analytical considerations compelled the incorporation of continuous variables into the theory. This culminated in modern probability theory on foundations laid by Andrei Nikolaevich Kolmogorov. Kolmogorov combined the notion of sample space, introduced by Richard von Mises, and measure theory and presented his axiom system for probability theory in 1933. This became the undisputed axiomatic basis for modern probability theory. However, there are alternatives, such as the adoption of finite rather than countable additivity by Bruno de Fineti, logarithms. The 17th century saw an unprecedented increase of mathematical and scientific ideas across Europe. Galileo observed the moons of Jupiter in orbit about that planet, using a telescope based on Hans Lippershey's. Tycho Brahe had gathered a vast quantity of mathematical data describing the positions of the planets in the sky. As Brahe's assistant, Johannes Kepler was first exposed to and seriously interacted with the topic of planetary motion. Kepler's calculations were made simpler by the contemporaneous invention of logarithms by John Napier and Jost Bürgi. Kepler succeeded in formulating mathematical laws of planetary motion. The analytic geometry developed by René Descartes, 1596 to 1650, allowed those orbits to be plotted on a graph in Cartesian coordinates. The Cartesian coordinate system is named after the French mathematician and philosopher René Descartes, who published this idea in 1637 while he was resident in the Netherlands. It was independently discovered by Pierre de Fermat, who also worked in 3 dimensions, although Fermat did not publish the discovery. The French cleric Nicole Oresme used constructions similar to Cartesian coordinates well before the time of Descartes and Fermat. Both Descartes and Fermat used a single axis in their treatments and have a variable length measured in reference to this axis. The concept of using a pair of axes was introduced later, after Descartes' La Géométrie was translated into Latin in 1649 by Frans van Schooten and his students. These commentators introduced several concepts while trying to clarify the ideas contained in Descartes' work. The development of the Cartesian coordinate system was a fundamental step in the development of the calculus by Isaac Newton and Gottfried Wilhelm Leibniz. The two-coordinate description of the plane was later generalized into the concept of vector spaces. Many other coordinate systems have been developed since Descartes, such as the polar coordinates for the plane and the spherical and cylindrical coordinates for three-dimensional space. Calculus is the mathematical study of continuous change. It is similar to geometry, which studies shape, and algebra, which studies generalizations of arithmetic operations. There are 2 major branches of calculus: differential calculus and integral calculus. Differential calculus concerns instantaneous rates of change and the slopes of curves. Integral calculus concerns accumulation of quantities and areas under or between curves. These 2 branches are related to each other by the fundamental theorem of calculus, and they make use of the fundamental notions of convergence of infinite sequences and infinite series to a well-defined limit. Infinitesimal calculus was developed independently in the late 17th century by Isaac Newton and Gottfried Wilhelm Leibniz. Later work, including codifying the idea of limits, put these developments on a more solid conceptual footing. Calculus is used in science, engineering, and social science today. Isaac Newton developed calculus in his laws of motion and universal gravitation. Gottfried Wilhelm Leibniz arranged these ideas into a true calculus of infinitesimals, which Newton initially accused him of plagiarizing. However, he is now regarded as an independent inventor of and contributor to calculus. His contribution was to provide a clear set of rules for working with infinitesimal quantities, allowing the computation of second and higher derivatives, and providing the product rule and chain rule in their differential and integral forms. Leibniz was more meticulous than Newton in his choice of notation. Newton was the first to apply calculus to general physics, and Leibniz developed much of the notation used in calculus today. Both Newton and Leibniz provided fundamental insights, including the laws of differentiation and integration, the inverse nature of differentiation and integration, second and higher derivatives, and the notion of an approximating polynomial series, graph theory. In mathematics, graph theory is the study of graphs, which are mathematical structures used to model pairwise relations between objects. A graph is made up of vertices, also called nodes or points, connected by edges, also called links or lines. It is important to distinguish between undirected graphs, where edges link two vertices symmetrically, and directed graphs, where edges link two vertices asymmetrically. Graphs are one of the principal objects of study in discrete mathematics. The paper written by Leonhard Euler on the Seven Bridges of Königsberg and published in 1736 is regarded as the first paper in the history of graph theory. This paper, as well as the one written by van der Monde on the night problem, carried on with the analysis situs initiated by Leibniz. Euler's formula relating the number of edges, vertices, and faces of a convex polyhedron was studied and generalized by Cauchy and Lhuillier, marking the beginning of topology. Normal distribution. In statistics, a normal distribution or Gaussian distribution is a type of continuous probability distribution for a real-valued random variable. Normal distributions are important in statistics and are often used in the natural and social sciences to represent real-valued random variables whose distributions are not known. Their importance is partly due to the central limit theorem. It states that, under certain conditions, the average of many samples, observations, of a random variable with a finite mean and variance is itself a random variable. This distribution converges to a normal distribution as the number of samples increases. Therefore, physical quantities that are expected to be the sum of many independent processes, such as measurement errors, often have distributions that are nearly normal. Some authors attribute the discovery of the normal distribution to de Moivre, who in 1738 published in the second edition of his The Doctrine of Chances the study of the coefficients in the binomial expansion of a plus b n. Euler's formula, named after Leonhard Euler, is a mathematical formula in complex analysis that establishes the fundamental relationship between the trigonometric functions and the complex exponential function. It is a fundamental concept in mathematics, physics, chemistry, and engineering. The physicist Richard Feynman called the equation our joule and the most remarkable formula in mathematics. When x equals p, Euler's formula may be rewritten as EIP1/0 or EIP1, which is known as Euler's identity, Bayes' theorem. In probability theory and statistics, Bayes' theorem, also known as Bayes' law or Bayes' rule, describes the probability of an event based on prior knowledge of conditions that might be related to the event. For example, if the risk of developing health problems is known to increase with age, Bayes' theorem allows us to calculate the probability of developing health problems for an individual of a known age, given their age and the known risk. Bayes' theorem allows the risk to an individual of a known age to be assessed more accurately by conditioning it relative to their age, rather than simply assuming that the individual is typical of the population as a whole. In probability theory and statistics, Bayes' theorem, alternatively Bayes' law or Bayes' rule, named after Thomas Bayes, describes the probability of an event. Based on prior knowledge of conditions that might be related to the event, Bayes' theorem allows the risk to an individual of a known age to be assessed more accurately by conditioning it relative to their age, rather than simply assuming that the individual is typical of the population as a whole. For example, if the risk of developing health problems is known to increase with age, Bayes' theorem allows the risk to be assessed accurately. Gauss's law. In physics and electromagnetism, Gauss's law, also known as Gauss's flux theorem, or sometimes simply called Gauss's theorem, is a law that states the relationship between the distribution of electric charge and the resulting electric field. In its integral form, it is unequivocal that the flux of the electric field out of an arbitrary closed surface is proportional to the electric charge enclosed by the surface, regardless of how that charge is distributed. While the law alone cannot determine the electric field across a surface enclosing any charge distribution, This may be possible in cases where symmetry mandates uniformity of the field. If no such symmetry exists, Gauss's law can be used in its differential form, which states that the divergence of the electric field is proportional to the local density of charge. The law was first formulated by Joseph Louis Lagrange in 1773 and Carl Friedrich Gauss in 1835, both in the context of the attraction of ellipsoids. This is one of Maxwell's equations, which forms the basis of classical electrodynamics. Gauss's law can be used to derive Coulomb's law, and vice versa. Group theory is the study of algebraic structures known as groups. The concept of a group is central to abstract algebra. Other well-known algebraic structures, such as rings, fields, and vector spaces, can all be seen as groups endowed with additional operations and axioms. Groups recur throughout mathematics, and the methods of group theory have influenced many parts of algebra. Linear algebraic groups and Lie groups are two branches of group theory that have made significant advances and have become subject areas in their own right. The early history of group theory dates from the 19th century. The 20th century saw one of the most important mathematical achievements in history, the classification of finite simple groups. This was the result of a collaborative effort that spanned more than 10,000 journal pages and was published between 1960 and 2004. Fourier analysis. Mathematics is the study of Fourier analysis, which is the representation or approximation of general functions by sums of simpler trigonometric functions. Fourier analysis grew from the study of Fourier series and is named after Joseph Fourier, who showed that representing a function as a sum of trigonometric functions greatly simplifies the study of heat transfer. Fourier analysis is a vast subject encompassing a vast spectrum of mathematics. In the sciences and engineering, the process of decomposing a function into oscillatory components is often called Fourier analysis, while the operation of rebuilding the function from these pieces is known as Fourier synthesis. For example, determining what component frequencies are present in a musical note would involve computing the Fourier transform of a sampled musical note. One could then resynthesize the same sound by including the frequency components as revealed in the Fourier analysis. In mathematics, the term Fourier analysis refers to both operations. The decomposition process itself is called a Fourier transformation. Its output, the Fourier transform, is often given a more specific name, which depends on the domain and other properties of the function being transformed. Moreover, the original concept of Fourier analysis has been extended over time to apply to more and more abstract and general situations. This general field is often known as harmonic analysis. Each transform used for analysis, see list of Fourier-related transforms, has a corresponding inverse transform that can be used for synthesis. Maxwell's equations. Maxwell's equations, also known as Maxwell-Heaviside equations, are a set of coupled partial differential equations that, together with the Lorentz force law, form the foundation of classical electromagnetism, classical optics, and electric circuits. The equations provide a mathematical model for electric, optical, and radio technologies, such as power generation, electric motors, wireless communication, lenses, radar, etc. These equations describe how electric and magnetic fields are generated by charges, currents, and changes in the fields. They are named after the physicist and mathematician James Clerk Maxwell, who published an early form of the equations in 1861 and 1862 that included the Lorentz force law. Maxwell used the equations to propose that light is an electromagnetic phenomenon. The modern form of the equations, in their most common formulation, is credited to Oliver Heaviside. There are two major variants of the equations. The microscopic equations have universal applicability, but are unwieldy for common calculations. They relate the electric and magnetic fields to total charge and total current, including the complicated charges and currents in materials at the atomic scale. The macroscopic equations define two new auxiliary fields that describe the large-scale behavior of matter without having to consider atomic-scale charges and quantum phenomena like spins. However, their use requires experimentally determined parameters for a phenomenological description of the electromagnetic response of materials. The term Maxwell's equations is often used for equivalent alternative formulations. Versions of Maxwell's equations based on the electric and magnetic scalar potentials are the preferred choice for explicitly solving the equations as a boundary value problem, analytical mechanics, or for use in quantum mechanics. The covariant formulation, on space-time rather than space and time separately, makes it clear that Maxwell's equations are compatible with special relativity. Maxwell's equations in curved space-time are compatible with general relativity and are commonly used in high-energy and gravitational physics. In fact, Albert Einstein developed special and general relativity to accommodate the invariant speed of light, a consequence of Maxwell's equations. The principle is that only relative movement has physical consequences. The publication of the equations marked the unification of a theory for previously separately described phenomena: magnetism, electricity, light, and associated radiation. It is now well established that Maxwell's equations do not provide an exact description of electromagnetic phenomena. Rather, they represent a classical limit of the more precise theory of quantum electrodynamics, set theory. Set theory is the branch of mathematical logic that studies sets. Informally, a set can be described as a collection of objects. While any kind of object can be collected into a set, set theory, as a branch of mathematics, is mostly concerned with those that are relevant to mathematics as a whole. The modern study of set theory was initiated by the German mathematicians Richard Dedekind and Georg Cantor in the 1870s. In particular, Georg Cantor is the founder of set theory. The non-formalized systems investigated during this early stage are called naive set theory. After the discovery of paradoxes within naive set theory, such as Russell's paradox, Cantor's paradox, and the Burali-Forty paradox, various axiomatic systems were proposed in the early 20th century. Of these, Zermelo-Fraenkel set theory. With or without the axiom of choice, it is still the best known and most studied. Set theory is commonly employed as a foundational system for the whole of mathematics, particularly in the form of Zermelo-Fraenkel set theory with the axiom of choice. Set theory is not only a foundational concept in mathematics, but it also provides the framework for developing a mathematical theory of infinity. It has numerous applications in computer science, including the theory of relational algebra. Its foundational appeal, along with its paradoxes, implications for the concept of infinity, and its multiple applications, have made set theory an area of major interest for logicians and philosophers of mathematics. Contemporary research into set theory covers a vast array of topics, from the structure of the real number line to the study of the consistency of large cardinals. Game theory. Game theory is the study of mathematical models of strategic interactions among rational agents. It has applications in all fields of social science, as well as in logic, systems science, and computer science. The concepts of game theory are used extensively in economics as well. The traditional methods of game theory addressed two-person, zero-sum games, in which each participant's gains or losses are exactly balanced by the losses and gains of other participants. In the 21st century, game theory has expanded to encompass a wider range of behavioral relations. It is now an umbrella term for the science of logical decision-making in humans, animals, and computers. Game theory did not exist as a unique field until John von Neumann published the paper on the theory of games of strategy in 1928 is a seminal work in the field of game theory. Von Neumann's original proof used Brewer's fixed-point theorem on continuous mappings into compact convex sets, which became a standard method in game theory and mathematical economics. His paper was followed by his 1944 book, Theory of Games and Economic Behavior, co-authored with Oscar Morgenstern. This book provided an axiomatic theory of utility, which reincarnated Daniel Bernoulli's old theory of utility, of money, as an independent discipline. Von Neumann's work in game theory culminated in this 1944 book. This foundational work contains the method for finding mutually consistent solutions for two-person zero-sum games. Subsequent work focused primarily on cooperative game theory, which is the analysis of optimal strategies for groups of individuals. These strategies are presumed to be enforceable agreements between the group members about the proper strategies.
We offer you deep historical information from history on YouTube channel. Subscribe. Now don't forget to turn on notifications.